limited ability to do non-standard circuits. So let me show you an example of a non-standard circuit and how I know that it doesn't fit into the categories that I've just talked about. Here would be an example. And in fact, it is the example that is on your homework. So the interesting thing to note about this is that this capacitor, this circuit, you have a capacitor and resistor in parallel. Okay? So that complicates things certainly. First of all, it would be incorrect to say that resistors 1 and 2 had any particular relationship to each other. They're not in series because they don't get the same current at all times, and they're not in parallel either. R1 and R2 are in parallel. R2 is in parallel with C. Now, the way that you know that the equations from before don't apply is that very clearly the total current in this circuit will never go to 0. So the total current will never go to 0. And the reason I know that is that even after the capacitor is full and no more current goes to this branch, there will always be some current because there's another way around. So what happens is at first, or during most of the time that this circuit is running, the total current goes through R1 and gets split. Some of it goes to fill the capacitor and some of it goes around to R2. But even after a long, long, long time, when the capacitor is full, there's still another way around. And if there's always going to be current, that means that there will always be voltage drop across resistor 1. And if there's always voltage drop across resistor 1, the capacitor can never climb to the battery voltage. Okay? So V across R1 never goes to 0, and so the voltage across the capacitor can never climb to that. So, what do you do? Well, certainly you can solve for the new exponential equations that govern this system, and in fact that is a challenge question on one of the problems, and it is quite a doozy because you're going to need to use your Kirchhoff's loop rules and junction rules, but then solve the simultaneous differential equations to get that. So that's why this is a bonus question or a challenge question, and something that you should understand the sort of the flavor of how it's done. But I'll tell you right now that what I expect you guys to do is to kind of work around a lot of what you can do easily. You guys are very experienced with what happens when things are in parallel, when things are in series, and you can say a lot about what happens in the circuit without having to solve for the exact functions. The key is, if you're asked about t equals 0, or after a very long time, you use the fact that at t equals 0, the cap is empty, and you can replace that with a short circuit, and then you can solve for what's going on. So you can functionally replace the capacitor with just a straight piece of wire, just like you would solve any of those short circuit problems on homework 5. And you can tell me what all the voltage drops and currents and all that business are. And then, when you have a full cap, you can think of it as an open circuit, and you can solve for what's going on. So really, the only thing that prevents you, that you're prevented from, if you don't have the full differential equation, is telling me what happens at t equals whatever time, right? Okay. So yes, you need this function if you want to know what goes on at a particular time. I think that on the homework question, I gave you the function. You'll notice it has some weird features. This is given on one of the homework problems, so you can certainly use it. But if it's not given, you can still say a lot. You just have to restrict your attention to t equals 0 and t equals infinity, and then you can, once you know that, you can reasonably even connect the graph of the exponential you just can't be asked for a particular, at t equals 380 milliseconds, what's going on, okay? So keep that in mind. And again, you know that you have one of these. If you wait forever, and you can clearly see that the total current doesn't run down to zero, because this function, by definition, it does. Here, you're discharging, and then there's nothing left to do. And here, once you've charged this, then the current shuts off. There's nowhere else for it to go. There's no parallel path around the capacitor, so once it's full, the current shuts off. So, you will find both standard and non-standard problems, both on the homework 7, and on the practice exams. So make sure that you can do identify which it is and be able to complete a problem like that. Are there any questions on this? Okay, so the final thing that is on homework number 7 is series and parallel caps. So I took a very detailed look at our upcoming schedule over the weekend, and what I've discovered is that we may be in a bit of a time crunch, and for that reason, I've done something that I don't really like to do. But what I'm going to do is I'm going to refer you to a video that I posted so that you can watch about, I think it's a little over half an hour of material outside of class. This is going to alleviate a time crunch we have coming up, and I'd rather reserve the lecture time for more challenging material. This is not some random YouTube lecture. This is a lecture by me, recorded in hopefully what you think is good quality. It is going through the series and parallel cases, which are very, very, very similar to resistors in series and parallel. Again, I hate doing this. I hate referring you to stuff outside of class, but it's going to save us some much needed class time, so I don't have to rush and scramble later on, okay? So there's a lecture video. I think it's like 38 minutes or something. And sometime this week, before homework 7 is due, of course, I would recommend that you watch it. So what I'm going to do here is I'm just going to summarize the results, okay? And this is not meant at all to be some sort of replacement or shortcut for watching this, but I want to give you just a little bit of a taste of the final results in my lecture, okay? So, first of all, here's Ohm's law. We are hopefully quite comfortable with it at this point. This is a law that we've done a lot of. It was basically the entirety of homework 5 was all about Ohm's law. We learned about resistors in series and parallel, all that stuff. And I want to put side by side with it the capacitance law. And it's just kind of shuffled around a little bit weirdly, but basically it's C equals Q over V, which is hopefully familiar to you from homework 6. The reason why I put these guys next to each other is because that allows me to draw the similarities between the two laws. V and V. I and Q. I is the flow charge, Q is just charge. And then there's some constant, and that constant is either R or 1 over C. So in that sense, knowing nothing else about any of the concepts or anything else, you can basically think of the new stuff as just a weird change of variables. So anytime you see voltage across the resistor, replace it with voltage across the capacitor. Anywhere where you see I, replace it with Q. Instead of the flow of charge, it's the amount of charge that has accumulated. Anywhere where you see R, replace it by 1 over C. And anywhere where you see P, replace it with U. literally give you the right answer for everything, pretty much. The only thing that you need to remember is there is an extra factor of a half in front of the potential energy formulas, instead of course, the power formula doesn't have the 1/2. Why is that? Well, the simple answer is that P is a rate. It's an instantaneous rate, whereas U is the amount of energy that's been stored up. So there's some averaging that happens during the charging process, which I talked about. That's where the half comes from. Okay? So, just like that, you get all your laws. By the way, the fact that R is replaced by 1/C actually flips the addition rules. So you guys remember that in series resistors, you just straight up add the resistors, right? Whereas if you have resistors in parallel, it's like that 1/, rule. Well, this flips them. So now the straight addition for series becomes the 1/, rule for capacitors, and vice versa. Where you used to do the 1/, rule for resistors in parallel, now capacitors in series, capacitors in parallel, you just add them. So it flips which one you do the 1/, rule and which one you do the straight addition rule. Okay. All the same stuff that we learned that in series, the bottleneck concept. The bottleneck concept is that all the action is at the large resistors. In series, you have to deal with everything. You don't have choices. But the large resistors, they have the most voltage drop, and they have the most power dissipated. Well, if R goes as 1/C, in series, the small capacitances are the bottlenecks. It's harder to charge a small cap. It's a bad cap. So, they have the largest voltage drops and they store the most energy. In parallel, we learned about the sideshow concept. Now that the idea is that you have choices, the choice is nicer to go the easy way. So we learned that these small resistors is where all the action is. They get the most current and dissipate the most power. Well, just like the small resistors are the easy way, R goes as 1/C, so the large capacitors are easier to charge. And all the action, once again, is at them. They will get the most charge. Charge is the equivalent to current, and they store the most energy. So, just like that, we're basically done. Again, not a substitute for watching the lecture video, but hopefully gives you kind of an overarching framework on which to hang these results. Okay? Okay, so I know that that's just an overview of basically the end to this video that you still haven't watched, but barring that fact, are there any questions? Okay, so I would recommend trying to find a little bit more than a half an hour at some point sooner rather than later. And of course, if you have any questions, please let me know on that as you finish up your homework 7. You're welcome to mark down in your notes, if helpful, that this is the end of the homework 7 material. And next thing, we're just going to go ahead, switch gears completely, and talk about magnetism. So I'm going to be talking about that imminently, clearing the board and switching gears completely. Does that change anyone's mind about asking any questions? All right, so magnetism. So, at first it's going to seem like this is a completely disconnected, separate topic, but the more we learn, the more we're going to realize that we are heading more towards magnetism, electricity, sharing traits, and finally becoming one and the same, two sides of the same coin. So we're going to take a little bit of a weird path. You may find it sort of backwards even. First, we're going to talk about magnetic field effects. Then move on to the causes. Then connections with electricity, and then actually I think before that in here we'll talk about bar magnets. And this seems kind of weird. First of all, bar magnets, like your refrigerator magnets or whatnot, most people's everyday common experience with magnets. If you think we talked about it first, we're going to talk about it last. The reason is that there's a lot that we need to understand before we can properly understand what's going on with magnetism. And during our journey, we will see how we can actually connect it back to our original electricity stuff that we've been talking about for most of the semester. All of this is, by the way, not on your second exam. In fact, this more or less describes the rest of the entire course. The cutoff, which is somewhat arbitrary for homework 8 and therefore exam 2, is magnetic field effects. So I generally like to group topics on the exams into some sort of sensible grouping, but in this case it's not that sensible. We'll be basically taking the magnetism unit, lopping a little bit off the front and throwing that onto exam 2 simply because otherwise there would only be 3 homeworks on exam 2, which is a little short, okay? So what we're going to do is basically for homework 8, the cause of a magnetic field will be a mystery, but we will just accept the fact that there is a magnetic field and we're going to explore how it can affect things. So here's what I'm going to do. I'm going to go ahead and put down a uniform electric field like this, and I'm going to put down a uniform magnetic field, and I'm going to compare. For magnetic field, by the way, we use B. I have no idea why. Someone look it up and tell me, okay? A lot of the other letters were already taken, I guess, okay? But we certainly understand what the concept is of a field, okay? So a field is something that allows us to talk about when we put something in a field, that something reacts to the local conditions. So I'm going to kind of think of this as like a virtual laboratory. I'm just going to start dropping charges in there and seeing what happens to them. Let's go ahead and start with the good old electric field. I'm going to have 1, 2, 3, 4, 5. These are no particular order, by the way. And I'm not dropping in 5 charges. I'm dropping in a single charge 5 different places and seeing what happens. And I want to just space them out so that I don't do everything on top of itself. I'm going to first try dropping a charge in at rest. Then I'm going to throw it with the magnetic field, with the electric field. I'm going to throw it opposite the electric field. I'm going to throw it perpendicular to the field. And I'm going to throw it at some random angle as the final case. So those are all the different, I want to see how all of those different charges react to the electric field, and then let me recopy them all over here. I want to do the same thing with the charge in the magnetic field. I want to see how they react. Again, this is not 5 charges for each field. It's 1 test charge that I'm dropping in various different places, and I just want to see how it gets affected by the local conditions of the field. Okay, well, the left-hand side, old news. We know that positive charges, how do they feel a force relative to the electric field?
Away.
They feel a force with it, right? So that's easy. We just copy the same rightward force on all of these guys. So I guess I'll do that in a different color. So this is a positive charge, so forces to the right, to the right, to the right, to the right, O-ring to the right, okay? And of course, that's because whatever the particular state of motion or lack thereof is, that's not in the rule for the force law, right? If you're a positive charge, it doesn't matter how you're moving, you feel a force to the same direction as the field if you're a positive charge and opposite the field if you're negative. That's all there is to the force law, okay? So let me remind you, the force law looked like this. This was the fancy vector version, but we rarely used it like that. We, of course, talked about the size, and then for the size, we, of course, strip off all directional stuff. So I pull the vector hats off of the force and field. That means that we're talking about vector magnitudes or sizes only. And then Q, of course, isn't a vector, but I put an absolute value sign around that because I don't want anything to muck up just looking at sizes and positive numbers. And then, of course, the direction part is that positive charges feel a force with the electric field, and negative charges feel a force against the electric field. This is all old news, okay? So we could certainly ask, well, what becomes of these charges? What does their subsequent motion look like? Well, here's what would happen. If you had a charge that started from rest and it got pulled to the right, what's it going to do?
Accelerate.
It's going to speed up going to the right, exactly. So, speeds up. So, speeds up. What if it's already going to the right and it gets pulled harder to the right? It's just going to speed up, but with a head start already, right? You've also done this problem on several occasions. What will happen to this charge?
It's gonna go and then stop and go back again.
Slow down, stop, turn around, and
Go back the same direction.
speed up, exactly. So the force and acceleration act opposite the motion until you have a chance to turn that charge around and speed it up. You've done that problem. You've done this problem too. I think it was on homework number 1. It was the Mach projectile motion problem, okay? So what's going to happen to this is it's going to get pulled to the right, but it already has a velocity that's perpendicular. So this will arc, kind of like a projectile thrown horizontally off a cliff. It'll have some sort of arc shape. Yes? Okay. And then finally, this, of course, is just getting a head start on that, but it will also arc because of that force, like that. So, that's all old news. That's just a summarizing what we know already. So let's go ahead and pretend we have a virtual laboratory. I'm going to tell you what happens if these charges are dropped like this same thing in a magnetic field. So let me tell you what the force is. This force, if you drop a charge at rest in a magnetic field, it just sits there at rest, which means what's the force?
0.
0.
Yeah.
And this charge that I throw along the magnetic field line, it does go that way, but at a constant speed. What does that mean the force is?
0.
0. It's just Newton's first law. It's just coasting off its initial throw, right? If you throw a charge upstream to the magnetic field, it will also go at constant speed, also with no force. So far, we have not seen one bit of evidence that the magnetic fields presence is in any way being registered by the charge. There's no force that it is able to exert. Clearly there's a big difference, right? The effects of a magnetic field on a charged particle are wildly different already. In all three of these cases, the force is zero. So, what do we have to do to get the charge to register the presence of a magnetic field whatsoever? Well, we get to these final two cases, and there will finally be a force. So, what is the direction of the force here? Well, this will curve, but it doesn't curve like this. It curves like this into the page. So it actually leaves the plane of the board, and for that, we are going to need to introduce some notation, because this is one of the first truly three-dimensional topics of physics. So, you imagine your Nerf arrow looks like this. Okay, if it's about to hit you in the eye, it looks like this. This is out of the page. And if you're retaliating and you're shooting it towards somebody, you'll see the crosshairs leaving you, and then behind it, the cone head. This is into the page. You guys should have seen this in Physics 250, yes?
No.
No?
We did, for WinHam we did.
For Adam you did? So, okay. Well, think Nerf arrow if you've never seen this, okay? Imagine this arrow either coming toward you or going away from you, okay? So, let me tell you the answer. If this particle curves into the page, it's because it got pulled that way. The force acts into the page. I'll show you momentarily how to get that direction. But if you take that for the moment as true, this final case we can actually do something with. We can break this into two components: the component of the velocity that's parallel to the magnetic field and the component that's perpendicular. Now, why would I want to do that? Well, I've already established, if you believe me on these guys, that if there is a component of the velocity that's parallel to the magnetic field, apparently the magnetic field could care less. So if you have a V parallel only, there's no force. So if this experiences any force, it's because of V perpendicular. Okay? So there is no force that can result from that component. So any force must come from this, and let me point out that the perpendicular part of this velocity is exactly the same direction as this, right? So if this velocity direction feels a force inward, then this same velocity direction, there must also be an inward force. So, what's the secret or the key to those last two cases? Why do they feel a force and the other ones don't? Well, if you are going to feel a force from the magnetic field, you have to have that your velocity either in part or as a whole cuts across the field line. Okay? In other words, you have to have a V perpendicular. Okay? So only if V perpendicular is at 0 will the force not be 0. That is an essential ingredient in experiencing a force from a magnetic field, is that your velocity has to either in whole or in part cut across the field line. Okay? So must cut across the magnetic field line. Either have at least a component or even your whole velocity being perpendicular to it. So, with that in mind, let me tell you the force law. And the force law, I'll start with the size, move on to the direction, and then show you how to encapsulate the two. The force law, it's exactly the same thing with the extra ingredient of V perpendicular. So instead of being just Q times E, or sorry, instead of just being Q times B now, it's QB with the extra ingredient, which I put into the middle, okay? For no good reason, okay? So instead of, we used to have just QE, now we have QB, but with an extra ingredient, which is that it matters how you move relative to the field. Over on the electric side, there was no such ingredient, right? That's why no matter how this thing was moving, the force direction was the same. But now there is an ingredient for motion. How is the charge moving relative to the field? Okay? Before I do anything else, I want to use this as an opportunity to do the units of magnetic field. So looking at this equation, I can solve for B, and I can work out what are the units of magnetic field. So let's do it. What are the units of force?
Newtons.
SI units, I should say. There's lots of units for force, but SI units are newtons. What's charge? Coulombs. And of course, that's where the story began and ended with electric field, right? That's why electric field unit was newtons per coulomb, right?
Mm-hmm.
Yes?
Yes, sir.
Okay.
E.
But there's one more ingredient here. What is velocity measured in?
Meters per second square.
Meters per second.
No, that's sorry.
So the units of magnetic field are not newtons per coulomb, but newtons per coulomb with a meters per second. So that's obviously kind of a mouthful, so let's abbreviate it. You certainly can abbreviate a coulomb per second. What's a coulomb per second?
Farad. Whatever.
It's an amp, right?
Oh, an amp.
So if you want, you can say newtons per amp meter. That still doesn't roll off the tongue. So let's just come up with a name for this. It's called a Tesla, or a capital T for short.
What the fuck?
That's units of magnetic field. SI units of magnetic field is a Tesla. I'll tell you right now that Teslas suffer from the same problem that a Coulomb suffers from. It's not an everyday amount of magnetic field. It's an extremely large amount. So you may be aware of sort of like powerful magnetic fields you might experience in everyday life, like you have to go get an MRI. An MRI, nothing magnetic is allowed in that whole room because it could become an extremely dangerous projectile once they turn the machine on. Okay? God forbid someone brings in a iron pair of scissors that could probably kill somebody because it would shoot across the room and impale the patient that was inside the MRI. That's about as powerful a magnetic field as you're going to see. And guess how big the magnetic field is? Maybe 3 Teslas. Okay?
Jesus.
It is Tesla is not a normal amount. It's a very large magnetic field. More commonly, you will see milliteslas, microteslas, nanoteslas, things like that. Okay, that's sort of normal. Same thing with the Coulomb. Okay? Okay, so that's a little bit of an aside on units. Let's get back to the law. And I do like this one for concepts, because it reminds me that in order to feel a force from a magnetic field, you need a perpendicular component of your velocity. You're not going to feel a force otherwise. That's why these first 3 cases, of course, the V perpendicular was 0. That's why the force was 0. The V perpendicular was 0 either because in the first case you don't have any velocity of any kind, or in the second 2 cases you had a velocity but it didn't have any perpendicular component. You were moving parallel to the field, either downstream or upstream, but there was no part of your velocity that was perpendicular. But as far as concepts go, the annoying thing about this is that while it reminds you that V perpendicular is necessary, you don't want to be doing SOHCAHTOA in every problem. That's just annoying. You don't want to be figuring out is V perpendicular V cosine theta or V sine theta or something like that. Let's just do the SOHCAHTOA once and never have to do it again, okay? So I go over here. Let me resketch this one right here. Here's my magnetic field. Here is my velocity. And then here are my components, v parallel, v perpendicular. And I'm going to call this angle theta. And then this will be v sine theta. So that's it. I go over here, Q, and then I'm going to take that sine and just throw it on the end. Is that okay that I reordered the terms? They're just multiplied anyway, right?
Sure.
So I took the v sine theta and I took the sine theta and put it on the end.
Mm-hmm.
Now, you might be highly skeptical of this, as you should be. Anytime that anybody tries to take a SOHCAHTOA and work the results permanently into an equation, well, you should point out, and rightly so, that why did I go parallel first, then perpendicular? Couldn't I have broken it up like this? This is v perpendicular and this is v parallel, right? There's nothing wrong with that. Right? You can break up a vector into components in either order. Yes?
Yeah.
Okay. So if I call this angle phi here, then this would be v cosine of phi. So that component that I want would now be cosine, right? Now, of course, these aren't the same angle either, so they would work out to be the same number, yes?
Yeah.
It's just a rectangle. But the question is if someone's trying to work a angle into a formula permanently, how do you know that you're picking theta? And so theta, you use sine. How do you know that you didn't accidentally pick phi instead of what you should be using cosine? Well, there must be something special about theta that there isn't about phi. And here's what's special about theta. Theta is the angle between the velocity in the magnetic field, and phi is not. Okay? So anytime anyone tries to work the results of a SOHCAHTOA into a formula permanently, you'd better believe there's going to be some very specific way of determining this angle. And that is the angle between the velocity and magnetic field. If you identify that angle, you are safely knowing you picked the right angle to put into the equation. You never have to worry about if it's sine or cosine because it will always be sine. So this makes for a much more computationally handy equation. You just throw in the ingredients, plug and chug. How much charge total? What's this overall speed? What's the strength of the field? And what is the angle between the velocity and magnetic field? And by the way, for those of you that might not remember this, when we're talking about the angle between two vectors, we measure them when they're placed tail to tail, okay? So it's a tail to tail thing, and that angle can range from a minimum of 0 to a maximum of 80. You measure the shortest angle. That angle can be 0 if they're pointed the same way. It can be 180 at the biggest. There's no bigger angle because if you're measuring the shortest angle between them, it starts closing again. This is not to be confused with vector addition. Vector addition, you can sometimes do it head to tail. We're not adding these vectors. These vectors are not addable. You can't add a velocity to a magnetic field. That makes no sense. It's like adding a meter to a second. What does that even mean? Okay? We're not adding these vectors. We are measuring the angle between them. We do that in the prescribed understood fashion, tail to tail, and measuring the shortest angle between them, which can range from 0 when they're pointed the same way to a maximum 180 when they're pointed opposite. Okay? So that right there is meant to be more of a kind of plug and chug. I just want my answer. Tell me how many newtons. Okay? Put in the entire amount of charge, how fast it's going, what field it's in, sine of, and then the angle of the velocity vector to the magnetic field vector. Okay, so that's more for calculating, okay? So for actual calculation, the conceptual thing is nice because it reminds you have to cut across the field line in whole or in part. And make sure you don't accidentally have a force where there is none, like in these cases. But when you actually get down to computing it, you don't want to have to do the SOHCAHTOA every time. You just did it once, you never have to do it again. Okay? Okay, so let's talk about the direction. So this is our first instance in this class, but by no means our last, of something called the right-hand rule. Hello? Is that okay? Okay. So this is inevitably used when there's full three-dimensional stuff. It requires you to have a right hand. And it is a mnemonic for getting the right answer. If you can come up with another mnemonic that uses something else, go for it. As long as it gives you the right answer, great. But right-hand rule is one of the things that you what right hand is one of the things you can use. So let me show you. Here's how it works. You slap the velocity with the palm of your right hand into the magnetic field. Your thumb gives the force direction. Now that can be a little bit awkward to describe, so it's a lot easier to show you. So here I have an example. Here is my velocity vector. I've already have it conveniently tail to tail with my magnetic field vector. And then, I couldn't find it. This is supposed to be the force. The flag fell off, okay? So here's what you do. You take the palm of your right hand and you slap V into B, your thumb gives the force, okay? So basically what I just did, you have to visualize that in your head in all sorts of different weird orientations, but that's all it ever is. Slap, force, okay? So, one of the things that goes wrong is this, okay? There's no karate chopping, okay? So that's not right, okay? You can't slap B into B with the top of your hand or the bottom of your hand, okay? It's got to be the palm, okay? Don't forget, palm. Here's another common mistake. I slap with the palm of my hand. It's all good. My thumb points down. What did I do wrong? I'm using my left hand. It's called the right hand rule, okay? So this is one of the few times in life that you lefties are at an advantage because you're sitting there writing with your left hand on the exam and doing the right hand rule with your right hand, okay? For everyone that's right-handed, put the pen down, do the right hand rule, go back to the paper. And by the way, I should point out that B and B don't have to be perpendicular, okay? But the force always will be perpendicular to both of those, okay? So that's how you know you did it, you have some confidence that you did it right. This ends up perpendicular to both of these, okay? So we'll do some more practice with that on Wednesday.